Hello, welcome to another video. In this case, we are going to make a continuation of the study that we have been doing on central forces. Okay, so, well, in this case, what we want to show is that planets move in elliptic orbits, okay? And why is that? Well, what we know by now is that planets are objects that are under the influence of central forces, okay? We have been studying central forces on previous videos, and we also showed that if we have a planet that is under a central force, well, this planet will move on a plane, okay? So all the motion of the planet will be focused on a plane, okay? That means that the coordinates that describe the motion of the planet will they will satisfy the plane equation, which is z equals ax plus by. Okay, we showed this on a previous video. Okay, but what we want to do now is that in particular case, well, planets will satisfy also the ellipse equation. Okay, that is what we want to show. So first of all, we need to remember that actually the central force that is acting on planets, well, it depends on the sun, okay? And it is given by the Newton's gravitational law. So if we remember, that equation tells us that the magnitude of F will be equal to K times M times the mass of the sun, where M is the mass of the planet, over R squared, okay? But we showed on a previous video that we can find the orbit equation of the object if we know what is the potential energy that that object has. Okay, so in this case, well, the terms that are here can be considered as constants. So we are going to just say that the force is equal to a constant over R squared. And we also know that a force, a conservative force, can be written as negative the derivative with respect to R of a potential that depends on R. Okay, so given this expression, we can easily conclude that the potential energy on a planet due to the central force caused by the sun will have the next form. It will be something like this expression over here, okay? So B is going to be equal to negative K over R. This is going to be the potential energy of the planet. Another thing that we showed on a previous video is that, well, the equation that we have to determine the orbit of an object under a central force is going to be the next. We are going to have plus minus the integral of d theta equals to the integral of L times dr over R squared square root of 2m times the energy, which is a constant, minus the potential B minus L squared over 2mr squared. Okay. In this case, L is equal to mr squared theta dot, which is a constant. Okay. This was also determined on the previous video. So in this case, what we need to do is to substitute this potential that we have here. We need to plug it here in the integral, and well, let's see what happens. At the end, we will see that that will be something similar, well, equal to the ellipse equation. But for now, we are going to start by taking the substitution u equals 1 over r. If we do this, then B is going to be equal to negative K times U. And if we calculate the differentials, well, we are going to see that dr is going to be equal to negative 1 over u squared times du. And And on the other hand, r squared is going to be equal to 1 over u squared. That is also something that we are going to need. Okay, so if we substitute this, we are going to have the next. This is going to be plus minus the integral of d theta equals to the integral of L times negative 1 over u squared du all over 1 over u squared times the square root of 2m times e minus ku minus L squared over 2m times 1 over u squared. Another thing that it is very important to mention is that, well, if we take this integral on d theta, well, it will be from some initial angle theta 0 to theta, okay? But we can just set theta 0 to be equal to 0, okay? So in this case, well, this would be like plus minus theta 0, but that will be, well, plus minus theta. And if we simplify what we have on this other integral, we are going to get that this is the integral for L times du over the square root of 2m times e plus ku minus L squared over 2m times u squared. Okay? And this, we are going to rewrite it as L times du over the square root of 2me plus 2m ku minus L squared u squared. Okay, so we are going to work out a little bit with that expression that we have here. This is, well, we can notice that this expression can be written as 2me minus L squared times u squared minus 2mku over L squared plus m squared k squared over L to the fourth plus m squared k squared over L squared. Okay, notice that if we multiply L squared times u squared, we get this term that we have here. And if we multiply this term by this term, we will get this term that we have here. And this term multiplied by L squared will cancel with this term here. So this expression that we have here is actually the same that we have inside the square root. Okay, but it's easy to notice that, well, all this expression that we have here can be written as u minus m k over L squared plus m squared k squared over L squared. So we can rewrite the integral as follows. This will be plus minus theta equals to the integral of L du over the square root of 2me minus L squared times u minus mk over L squared plus m squared k squared over L squared. So to evaluate this integral, we are going to make the next change of variable. We are going to define u minus mk over L squared as 1 over L times the square root of 2me plus m squared k squared over L squared, and all this is going to multiply a new variable which is going to be beta. Notice here that all this expression, well, is a constant. Okay, we are involving m, e, and L and k. They are all constants. So, and we are relating the variable u with the variable beta. Okay, so if we take, for example, the derivative of u with respect to beta, well, this is just going to be negative 1 over L times the square root of 2me plus m squared k squared over L squared sine beta. Okay, so if we substitute this on the integral, well, we are going to get that plus minus theta is going to be equal to the integral of L times du, but du is going to be negative 1 over L times the square root of 2me plus m squared k squared over L squared sine beta d beta all over, well, the square root of 2me minus L squared times, well, this whole thing here. This is 1 over L times the square root of 2me plus m squared k squared over L squared cosine beta squared plus m squared k squared over L squared. If we keep simplifying stuff, we are going to get that this is the integral of negative the square root of 2me plus m squared k squared over L squared sine beta d beta all over the square root of 2me minus, well, this L squared will cancel this L, that is to the 2 power. Okay, so this is just going to be minus 2me plus m squared k squared L squared cosine squared beta. Okay, just by canceling the square root here with the squared here, and then plus m squared k squared over L squared. And I need to put the parentheses here. Okay, so we can continue with this. Yeah, and recall that, well, from the beginning I forgot a minus here. Okay, so this is minus, 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 and finally this is going to be plus sign. Okay, so if we rewrite this, this is going to be the integral from the square root of 2me plus m squared k squared over L squared sine beta d beta all over the square root of 2me minus 2me cosine squared beta minus m squared k squared over L squared cosine squared beta plus m squared k squared over L squared. Okay. Now notice that this can be rewritten as the next. This is going to be the square root of 2me plus m squared k squared over L squared sine beta d beta, and on the denominator we are going to have here that this is 2me times 1 minus cosine squared beta plus m squared k squared over L squared times 1 minus cosine squared beta also. And this can be factored again. Here we are going to get that the square root of 2me plus m squared k squared over L squared will multiply 1 minus cosine squared beta. But actually 1 minus cosine squared beta, well, it will be sine squared beta. Okay, so this is sine squared beta, and here we have the same 2me plus m squared k squared over L squared. We have a sine beta here, d beta here, and with the square root, well, this squared will be cancelled. Okay, so we are just going to get that this is the integral of d beta, because this term cancels with this term over here also. So finally we get that plus minus theta is equal to the integral of the beta, which is actually beta. Okay, but recall that we made a change of variable given by this expression over here. Okay, so we just found that beta is equal to plus minus theta. Okay, so we can just put theta inside here, and well, that will be the final result we are going to get if we do that, well, 1 over r is equal to mk over l squared plus 1 over l times the square root of 2me plus m squared k squared over l squared times cosine theta. In a more general way, if, for example, theta 0 is different from 0, we are going to get the next result. mk over l squared plus 1 over l times the square root of 2me plus m squared k squared over l squared times cosine of theta minus theta 0. Okay, well, so we are very close to get the equation of the orbit of a planet, but now you need to notice now that we are going to try to rewrite this expression that we have here by noticing the next. We are going to factor mk over l squared and see what happens. Okay, notice that mk over l squared times 1 plus the square root of 1 plus 2el squared over mk squared, times cosine of theta minus theta 0. Well, it's actually the same to this expression that we have here, okay? For example, what happens if we multiply? Well, let's notice that this is going to be mk over l squared plus mk over l squared times the square root of 1 plus 2el squared over mk squared cosine of theta minus theta 0. Okay, but to plug this expression here, we can just raise to the second power and then take the square root. We can multiply mk squared over l squared inside the square root, so we are going to get mk over l squared plus the square root of m squared k squared over l to the fourth plus, well, m squared over m, which is going to be m, then k squared over k squared will be cancelled, then e at 2, and then l squared here, and all these multiplies cosine of theta minus theta 0. If we factor an l squared here, well, we get that this is mk over l squared plus 1 over l times the square root of m squared k squared over l squared plus 2me cosine of theta minus theta 0. So we have shown that this thing that we have here is equal to, well, this thing here by this process. Okay, so we are going to rewrite the equation like this. So finally we get that 1 over r is, well, all this. Let me copy. Okay, so we got this equation over here, which it isn't maybe so pretty, but you need to notice that again, well, all this expression here is a constant because, well, it just involves constants, so we can rename it. In this particular case, well, we are going to see that the result is going to be an ellipse, and a very famous concept regarding ellipses is, well, the eccentricity. So that is going to be our motivation to name that expression with the letter E. We are going to define the eccentricity as E equals the square root of 1 plus 2 times E L squared over mk squared. Okay? So if we rewrite the equation, we are going to get 1 over r equals mk over L squared times 1 plus E cosine theta minus theta 0. Now, if you have studied a little bit regarding conic sections, well, you need to know that if you know the eccentricity, well, you can have three cases. One is that when E is equal to 1, in this case, you will have a parabola, okay? If the eccentricity is equal to 1, then the conic section is a parabola, okay? If the eccentricity is greater than 1, it will correspond to a hyperbola. And if the eccentricity is less than 1, then you will have an ellipse, which is going to be our case, okay? But what do we need to have, well, an eccentricity less than 1? Well, we see that if E is less than 1, then looking this expression, we see that then the energy E needs to be less than 0. In that way, we are going to be subtracting this quantity that we have here. Then we are going to get a number that is less than 1. And then the square root of a number that is less than 1 will also be a number that is less than 1. So that is a very important fact. So looking that the eccentricity is going to be less than 1, that means that the energy is going to be less than 0. Now, to simplify this, well, we are going to explain the next. If we have the reference system here, for example, let's say that the motion starts at theta 0 equals to 0, we can just rotate the axis to establish that the x-axis will match with the motion of the position. This is going to be the same as saying that, well, theta 0 is going to be equal to 0. Okay, so we are going to rotate the axis just to take theta 0 equals to 0 and to simplify the equation that we just found. That means that 1 over r is going to be mk over L squared times 1 plus E cosine theta. Okay, now in that case we can draw the motion of the object. For example, let's say that it is in this position here. Well, it will move on this trajectory, for example. So we need to notice that we have here an inverse relation between r and well, what we have here, mk over L squared times 1 plus E cosine theta. Okay, that means that when r is minimum, well, all this expression is going to be as big as possible. Okay, but to make that possible, well, we need to have cosine theta equal to 1. Okay, to make this whole expression to be as big as possible. Okay, that means that theta is going to be equal to 0. Okay, if cosine theta is equal to 1, then theta is equal to 0. Okay, so in that case, when we have the minimum r possible, we are going to have this expression. 1 over r minimum is going to be equal to mk over L squared times 1 plus E. And well, by the same reason, we are going to have that the R maximum is going to be obtained as follows. It will be mk over L squared times 1 minus E. Looking that, well, when we have the R maximum, we are going to have the smallest quantity on the right hand side of this equation. that means that, well, this needs to be -1, and if cosine theta is -1, that means that theta is going to be equal to pi. Okay, so then we will have 1 minus e here. Now if we draw our ellipse, well, we know that ellipses have major and minor semi-axis. Well, we are going to name the major semi-axis, well, let me redraw this just for not to confuse. We know that we can divide the ellipse like this, for example, and we know that the major semi-axis is this. We can rewrite this as b, for example, for the minor semi-axis. Well, we know that a is going to be the major semi-axis. So this whole axis that I'm underlining here can be specified as 2a, okay? But for example, if we have the focus here, the reference system here, in that case, this will be our R minimum, okay? And R maximum will be this, okay? So it is very easy to notice that 2a is going to be equal to R minimum plus R maximum. And by the expressions that we found recently, this one and this one, well, we can calculate what is 2a. We know that 2a is going to be equal to R minimum, so this is going to be L squared over mk times 1 plus e, and then R maximum, which is L squared over mk times 1 minus e. Okay? Okay, so we can factor an L squared over mk to get 1 over 1 plus e plus 1 over 1 minus e. This is going to be L squared over mk times, well, 1 minus e plus 1 plus e over 1 plus e times 1 minus e. And this is that 2a is going to be equal to L squared over mk. We can cancel these two e's to get 2 here, and then 1 minus e squared here. We can cancel these 2's to get that a, which is the major semi-axis, is going to be L squared over mk times 1 over 1 minus e squared. Okay, but we found that the eccentricity is defined as the square root of 1 plus 2 el squared over mk squared. Then if we plug this here, we are going to get that a is going to be L squared over mk times 1 over 1 minus this thing raised to the second power, and that is going to be 1 plus 2el squared over mk squared. Okay, and that leads us to a equals L squared over mk times 1 over negative 2el squared over mk squared, okay, which is going to take us to say that a is going to be negative k over 2 times e. So very interesting noticing that the major semi-axis of the ellipse that the Earth makes around the Sun, it will depend on the total energy of the Earth. It has sense, looking that we saw that the total energy is less than 0, and that means that, well, with this negative, then a is going to be bigger than 0. okay, which is very well. We should expect that a is bigger than 0, looking that we have an ellipse. Okay, but yeah, just to finish this video, again, recall that this is the important result of the video. This is a relation between the radius, well, the distance between the Sun and the Earth, okay, which is r, and the angle that is making the Earth with the x-axis of the reference system that we are using. But what you need to notice here is that this is actually the polar representation of the equation of an ellipse, okay? When the eccentricity is less than 1, this polar equation will represent an ellipse, okay? So we got the polar representation of an ellipse, okay? That means that the Earth, well, makes an ellipse around the Sun.